Well, good day, ladies and gentlemen. We have finished our second test. Hopefully each of you took it, and results were from 100% correct to less than that. And what we have to keep in mind is that we have one more test to go. That'll be a third of your test grades. So one more test to go, and it will cover what we start today through the end of the semester. So only what we covered today through the end of the semester will be on the second test. This week we only have two sections to go over. 7.1, which is exponential functions and their graphs, and 7.3, which is logarithmic functions and their graphs. So we're going to start with exponential functions and their graphs, and I think we're going to find that this is not very challenging. Please do your best to, number one, watch the video. Number two, look at the notes that I will post on Quickly content on your Blackboard, and that should give you every advantage to do this 100% correctly. So 7.1, exponential functions and their graphs. Here we go. You and I have looked at functions before that looked at something like this. F of x equal x squared. Remember that guy? That was the old parabola, upward turning parabola. F of x equal x cubed. You've got this on your parent or basic functions. Looks something like that. F of x equal x to the fourth. Looked basically like x squared, except it was a little bit more intense. And so we've looked at examples of functions where the x was taken to some power. We've even looked at the function f of x equal x to the 1/2 power. You might not remember, but x to the 1/2 power is the square root of x. That looks something like that. So basically we have looked at x taken to some power. When we look at exponential functions, we're going to change the location of our variable x. Here's an example of an exponential function. F of x equals some number to the x power. Notice that what changes is the exponent itself changes. This is my x value. So when I substitute y for f of x, I'm going to be looking for something to the xth power, and I will be picking x's to find out what that is. One thing we got to keep in mind is that a must be positive. You can read reasons for that, but trust me, A's got to be positive. The basic reason it can't be negative is because if I have a negative number to something like the 1/2 power, that means the square root of a negative number, and that does not have a real number value. So don't need to worry about this. Just keep in mind that A is going to be a positive number. All right. Let's see what we discover when we graph f of x equal something to a power. Let's pick an a. Let's find this exponential function f of x equal 3 to the x power. And let's discover what the graph of this thing looks like as we substitute various values for x. And we're going to do the same thing we've done before. We're going to have an x and we're going to have a y. The reason I have a larger y area is we're going to have to figure out what y is. All right, let's pick some x's. And remember, y is going to be 3 to the xth power. So I'm going to be picking some x's. My y value is going to be 3 to that power. So let's start with 2. So y is going to be 3 to the 2nd power. What's that? Oh yeah, that's 9. Let's pick 1 for x. Y will be 3 to the 1st power. y is going to be 3 to the first power. What's 3 to the first power? That's just 3. Let's pick 0. Y is going to be 3 to the 0 power. And I'm sure you haven't forgotten that 3 to the 0 power, 2 to the 0 power, 7 to the 0 power, anything, any real number to the 0 power is going to be 1. All right, let's go -1. I can pick negatives for my x because I can find out what y is. Y is going to be 3 to the -1 power. Here's where I have to remind myself. 3 to the -1. What is that? Oh yeah, one way I can do this is to think of it like this. I can move a factor to the other part of the fraction if I change the sign of my exponent. This is just 1/3. So 3 to the -1 power is just 1/3. Let's try -2. We're going to pick -2 for x. So y is 3 to the -2 power. I do the same thing. Just move it downstairs and change the sign of my exponent. 1/3 squared, that's just 1/9. All right, let's take a look at what this guy is going to look like. Got the points drawn here. When x is 2, y is 9. 2, 9. When x is 1, y is 3. 1, 3. When x is 0, I get 1. When x is -1, I get 1/3. When x is -2, I get 1/9. I went ahead and went a little further. When x is -3, I get 1/27, 1/81. You can see what's happening here. It's getting closer and closer to the x-axis, a 0 value for y, but it's never going to touch it. It's what we call asymptotic to it. And so the graph is going to look basically like this. It's going to go right through the point 0, 1. That's what it looks like. So that's a picture of the graph f of x equal 3 to the xth power. And by the way, f of x equal 2 to the x power looks basically the same thing. A little smoother. 4 to the x power, be a little steeper. So it's basically going to have this look for f of x equal some number to the x power. But will that always be the look? Let's check something else out. What if the number that I picked for a is not in fact greater than 1, but is in fact less than 1? Let's pick a value like 1/3. So instead of f of x equal 3 to the x, let's see what f of x equals 1/3 to the x is going to look like. And let's see if it basically takes the same shape. Let's see what happens. Well, once again, I'm going to be picking some x's very cleverly, making it easy on myself, and finding some y's. F of x is the same as y, so y equals 1/3 to the xth power. So again, let's start with 2, 1, 0, -1, -2. Really good values to pick when you're evaluating a exponential function just because it works so nicely. All right, so y is 1/3 to the x. If I pick x is 2, y is 1/3 squared. That means 1/3 times 1/3. That means 1/9. If I pick 1 for x, y is 1/3 to the first power. That's just 1/3. If I pick 0 for x, y is going to be 1/3 to the 0 power. Oh, don't forget, any real number to the 0 power is going to be 1. Hey, interesting thing to note. Every one of these exponential functions is going to go through the point 0, 1. Unless, of course, it is transformed in some way. But every basic exponential function will go through the point 0, 1. Why? Because when I evaluate any number at 0, I'm going to get 1. All right, here's where it gets a little sneaky. x is -1. I got 1/3 to the -1 power. All right. We could use some principles we've already used, or I could show you a new one, and I think this new one works really nicely if you have a fraction to a negative power. And here's the principle that applies. Any real number to a negative power is the same as its reciprocal to the positive power. And I know how to deal with positive powers. Now, I'm hoping you're writing that down, and I'm hoping you're going to be careful as we interpret this. We're going to use a real number, real world example, this one right here. Any real number to a negative power, that's what we got here, any real number to a negative power is the same as, and you know mathematically that means equals, is the same as its reciprocal. What's the reciprocal of 1/3? 3/1, or just 3. Is the same as its reciprocal to the positive power. So -1 becomes +1. So any number to a negative power is the same as its reciprocal to the positive power. What's 3 to the first power? Why, that's 3. So 1/3 to the -1 power is simply 3. Okay, let's do this one. Let's let x be -2. Y is 1/3 to the -2 power. I wonder what that's going to be. Let's find out. Let's use this principle. Any real number to a negative power is the same as its reciprocal, there's the 3 again, to the positive power. Hey, 3 squared? No problem, I can handle that. 3 squared is 9. All right, so here's what we got here. Here is our second function. It's f of x equal 1/3 to the x power. And let's see what these points are. I get 2 1/9, 1 1/3, 0 1. There's that old faithful point, 0 1. -1 is 3. And -2 turns out to be 3, 4, 5, 6, 7, 9. Well, what do you know? Look at that. F of x to the 1/3 power. F of x, equals 1/3 to the x. X being my exponent, looks exactly like f of x equals 3 to the x, except it's the mirror image of it. 1/3 to the x looks like this. Goes through my standard point 0 1, and then it flattens out. Closer and closer and closer to the x-axis, but never getting there. Now here's what we're going to observe in general. F of x is equal a to the x if a is greater than 1, something like 1.5, 2, 3, 4.7, anything greater than 1, it's going to basically have this look right here. If, however, remember a's got to be positive, so that means if my a is between 0 and 1, stuff like 1/2, 1/3, 2/5, 0.7. If it's somewhere between 0 and 1, it's going to basically have this look right here. So if my base, my A, is a number between 0 and 1, the exponential function will have a look like this. If my base, my A, is greater than 1, anything greater than 1, it's basically going to have a look like that. We're going to use that when we start identifying what our graphs look like on Hawks. All right, let's look at some of our Hawks problems and see if we can figure out the answers based on what we just observed with these two graphs. Here's the first one. Choose the graph that represents 5/2 to the x power. Now you and I, and by the way, Hawks is going to give you 4 pictures and you're going to pick one of them. You've done that before, right? So you're going to have 4 pictures and you're going to pick one. First thing we're going to notice, this guy is greater than 1, isn't it? My base is greater than 1. There's a temptation to go, oh, that's a fraction. That must be somewhere between 0 and 1. No, put that in your calculator. 5 divided by 2, this is basically, another way to say it, 2.5 to the xth power. Now, I know that when my A is greater than 1, it's going to have a look like this. So my graph is basically going to look like this. I know it's going to go through the point, because this is a standard representation of an exponential graph. It's going to go through the point 0, 1. In fact, you can just find some points that you'll be able to find an x and a y for as you look at your 4 graphs. Another way to say it, y is 2.5 to the x power. So let's pick some x's. Let's say 2. And you're going to have to put this in your calculator, probably. 2.5 squared turns out to be 6.25. Let's try 1. 2.5 to the first power turns out to be 2.5. And let's try one more, 0. 2.5 to the 0 power, of course, is going to be 1. So you are looking for a graph that basically has this look and goes through these points. That's the one you're going to choose. All right. Next problem. Choose the graph that represents m of x is 4 to the x minus 2 power. All right, here's where we're going to have to remember what our translations or transformations of functions look like. This, I believe, was section 4.4 in what we've already done. You remember the horizontal shifts, the stretching and compressing, the reflections, the vertical shift. Let's just review for just a second to remind ourselves what this looks like. Let's take another function that's not exponential, like f of x equals x squared. Remember this guy? In unadorned form, plain old basic function, x squared is just a parabola. It goes through the origin. But remember what we can do to this guy. We can do what's called horizontal shifts. And that's horizontal shift. When I do a horizontal shift, I alter the x itself. That is, I either add or subtract from the x itself. Something like this. F of x equal x minus 2 squared. squared. See, I actually changed what's being squared. I changed the x itself. That's a horizontal shift. And remember, this is kind of contrary or counter to our intuition. My intuition says, hey, -2, I'll bet it moves that to the negative direction, does just the opposite. So a -2 horizontal shift would move this whole graph 2 places to the right. +3 would move it 3 places to the left. So that's the first thing you look for. And remember, I have to look for these transformations in an order. First thing I look for, horizontal shift. Is the x itself altered? Second thing I look for is a stretching or compressing. That's when there is a coefficient for x, a number in front of x. For instance, f of x equals 2x squared, a coefficient in front of x. All the stretching or compressing does is either thin up my parabola or spread it out. But it doesn't change the general shape of my graph. It's still a parabola. So this is not that important as far as identifying what happens to the graph. It just changes the shape a little bit of the graph itself. The third kind of transformation is a reflection. That is the mirror image of the graph over either the y-axis or the x-axis. And of course there's two kinds of reflections. There is a y-axis reflection, and that happens when the x is made negative. X itself is made negative. So in this case, it would look like something like this, my guy right here. F of x equals -x squared. Now notice the x itself has been made negative. This is very subtle difference, but the y-axis reflection, the x itself, the thing being squared, is made negative. The x-axis reflection, the whole function is made negative. So I still get f of x equals x squared. It's just that I make the whole function negative. That's a subtle difference. In this case, it's very subtle. In the one we're going to be looking at, it's not so subtle. But a y-axis reflection, when the x is made negative, it flips the graph over the y-axis. In this case, it wouldn't change it at all. This part flips over here and looks like that. This part flips over here and looks like that. If I had the x-axis reflection where the whole function is negated, it would flip the whole thing upside down over the x-axis. The final kind of transformation that we look at is, of course, not a horizontal shift, but a vertical shift. And that happens when I add or subtract at the end of the function. End of the function is the key part. Horizontal shift, I alter the x itself. I add something to what's being squared, or I subtract something from what's being squared. Vertical shift, looks like the plain old guy, except I add something at the end. Or I subtract something from the end. And this, of course, moves the whole graph up or down. Up, just like what you'd think if it's plus, down if it's minus. So these are the transformations we're going to be considering when we look at a graph like this. So let's look at this graph to start with. Let's think of it as a y. So y equals 4 to the x minus 2. And we're actually going to be taking a couple of points, a couple of x's, and find out what y is in a minute. But basically, this guy is going to look like this, isn't it? Basically, it's going to look like this. When my base is greater than 1, f of x equals 3 to the f of x equals 3 to the x, 2 to the x, 4 to the x. So the basic function is f of x equal 4 to the x. And it's going to look basically like this, right? But something's been done to this. Let me go ahead and give you a couple of points on f of x equal 4 to the x. Let's do some easy ones. Y equal 4 to the x. Let's do 2, 1, and 0. Y equals 4 to the 2, or 4 squared, that's 16. Y equals 4 to the first power, or 4. Y equals 4 to the 0 power. There's our old friend, 0, 1. So it goes through 0, 1, 1, 4, 2, way up here at 16. And then it's going to go just like this. So that's what my basic function looks like. And I'm wondering what my transformed function is going to look like. Well, it's going to take this graph and let's see what's done here. Something has actually been changed with the x itself, hasn't it? If I alter the x itself, I'm going to move it horizontally, left or right. I have done that. I have changed the x itself, no longer 4 to the x, but 4 to the x minus 2. Remember what a minus 2 horizontal shift does? That's right, 2 to the right. So this says move the graph 2 to the right. So instead of having a point 0, 1, I've got the point 1, 2, 1. Instead of having the point 1, 4, I have the point 1, 2, 3, 4. And 4, 16. And it's basically going to go crazy, getting closer and closer to the x-axis. So that's the important thing to look for when I choose the graph. It's going to go through the point 1, 2, 0. It's going to go through the point 1, 2, 3, 4. Look for those 2 points and this general shape, and you'll have it good. And what you can always do if you wanted to find some points is substitute some points right here. Y equals 4 to the x minus 2. Pick some x's and some y's. Let's pick 3. 3 minus 2 is 1. 4 to the first power is just 4. Hey, there's that point, 3, 4. Let's pick 2. 2 minus 2 is 0. 4 to the 0 power is 1. Hey, there's the other point we're looking for, 2, 1. All right, so here we go with some points that let us know in general, or specifically, what our graph looks like. The fact that my A is greater than 1 lets me know in general what it looks like. All right, let's keep going. I'm going to skip number 3 and go to number 4 because it's still dealing with graphing. Choose the graph that looks like this feller right here. All right, notice my A. My A is between 0 and 1. Since my A is between 0 and 1, I know in general my graph is going to look like this to start with. So my basic graph function is going to be, it's going to go through the point 0, 1, like they all do, and look like this. That's what y equals 1/5 to the x power would look like. But please notice I have some transformations. Now we're going to have to be careful in dissecting this transformation. Here's an observation. Have I added or subtracted something to the x itself? That's confusing the way this looks. So let's change the way this looks. Instead of q of x equal 1/5 to the 3 minus x, I'm going to just switch these guys. Q of x is 1/5 to the negative x plus 3. Everybody see that 3 minus x, see the negative x right there? See the positive 3 right there? 3 minus x is the same as negative x plus 3. This gives me a better understanding of my transformations. So let's consider the transformation first. Has there been a horizontal shift? Was something added or subtracted to the x itself? To which you would say, yeah, something was added or subtracted to the x. So I have a horizontal shift. See that plus 3? That means I move it 3, which direction? Left or right? 3 to the left. Remember, it's just the opposite of what you think. Plus 3 means I move it 3 to the left. So basically, this graph is moved 3 to the left. All right, let's check it out. Number 2, a stretching or a compressing. Is there a coefficient other than 1 in front of x? No, no stretching or compressing. 3, reflection. Is there a y-axis reflection? Has x itself been made negative? Yes, x itself has been made negative. What that means is this new graph is going to be reflected over the y-axis. So my new graph, after both of these reflections, is going to be something like this. How about an x-axis reflection? Was the whole function made negative? No. If there was a negative sign in front of the whole function, I would also flip it over the x-axis. But I do not have an x-axis reflection. And finally, is there a vertical shift? Was something added or subtracted at the end of the function? No. So there's no vertical shift. So this is basically what I have after my 2 translations. Number 1, I moved it 3 units to the left. And number 2, I reflected it over the y-axis. I took a mirror image of it. So I'm basically going to be looking for a graph that looks like that. And if you want to find a specific point that's on this graph, the best way to do it is to choose the x that gives us a 0 exponent. So if I want to pick a convenient x and y, I'm going to pick an x that makes this whole thing 0. So -3, if I let x be 3, -3 plus 3 is 0. 1/5, anything to the 0 power is 1. So this guy goes through the point 1, 2, 3, 1. Why isn't that -3, 1? Hey, I picked 3 for my x. 3 is my x. The negative of that, -3. -3 plus 3 is 0. 1/5 to the 0 power is 1. So you're looking for the graph that has this general shape and this exact point. All right. Now let me go back to number 3. The rest of our problems, I believe, and let me check real quickly. The rest of our problems are going to basically be in the format, solve the following exponential equation. That look kind of confusing? Here's what we're going to do to solve our exponential equations. We're going to use a property of exponents, and it's going to look like this. Let me just write an example here, and you see if you can figure out exactly what I'm going to say. If I have something that says like 2 to the 7th power equals 2 to the xth power, care to guess what x is equal to? That's exactly right. It's going to have to equal 7. And here's the principle. If I have the same base in an equation, then my exponents must be equal. So if you have 2 to the 7th equal 2 to the x, what do you know? 7 must equal x. Well, how about if it's a little more sophisticated than that? How about if you had x to the 7th equals 2 to the x plus 1? Same thing. I've got the identical bases. That means my exponents must be the same. So 7 must equal x plus 1. Subtract 1 from both sides. X must be 6. Hey, I solved the equation. I found out what x is. It can get more sophisticated. How about if you had 2 to the 7th equals 2 to the 3x plus 4? A little bit more complicated, but the same exact principle. If I have the same base, my exponents must be equivalent. So 7 must equal 3x plus 4. And you can solve that equation. Minus 4, minus 4. 3x is 3. X must be 1. Hey, what do you know? I solved the equation. All right, here's where it gets a little tricky. What if you had something like this? 2 to the 7th equals 8 to the xth power. Uh-oh, you say, I no longer have the same base. Here's where you're going to make a substitution to get us right back to this place where we want to be. Now, a while back, I gave you a little chart. Hopefully you wrote it down, but if not, you could probably recreate it. It looks something like this. It's what some very basic numbers are raised to powers. 2 squared, 2 to the 3rd, 2 to the 4th, 2 to the 5th, etc. 3 squared, cubed, to the 4th, etc. So for instance, If I wanted to make a substitution in the place of 8, I could substitute 2 to the 3rd power. And that is precisely what I want to do, because I want to have my base, my common base, to be 2 to some power. So I'm going to make a strategic substitution. In the place of 8, I'm going to substitute 2 to the 3rd power. And by the way, all these notes and this graph I'm going to put on quickly content, so you'll have this graph again if you lost it or don't want to recreate it now. So 8 is the same as 2 to the 3rd power. So in the place of 8, I'm going to substitute 2 to the 3rd power. Now remember, I'm just substituting for the 8. 8 is the same as 2 to the 3rd power, but the right side of my equation is this to the xth power. So instead of 8 to the xth, I have 2 to the 3rd to the x. All right, let's keep going. I have a principle, a property of exponents that says if I have a power to a power, what do I do with these exponents? Yeah, I multiply them. So that's 2 to the 3x. Hey, I'm where I want to be now. Got the same base. Exponents must be equivalent. So 7 must equal 3x. Divide both sides by 3. X is 7/3. Now you have to admit this is not a solution that most of you would have come to if you just looked at an expression like this. Hey, 2 to the 7th equal 8 to the x. I'll bet you x is 7/3. Very few of you would come to that conclusion. So what we do is we make a strategic substitution so that we have exactly the same base. When I have exactly the same base, my exponents must be equivalent, okay? Set them equal to each other, solve for x, and I got it. Let's use that principle to solve for this guy right here. And what some of you probably are observing is, hey, those are a couple of chart numbers. 32 and 16, they're a couple of chart numbers. They are 2 to some power. So I'm going to make a double substitution after I do one thing. My first step is going to be to isolate the exponential expression. The thing taken to a power, the exponential expression. Hey, if they're both exponential expressions, isolate them from each other. A little social distancing here with my two terms. So I'm going to isolate the exponential expression. 32 to the x, move to the other side, change the sign, equals 16. All right, here's where I'm going to make strategic substitutions. In the place of 32, I'm going to put 2 to the 5th power. But remember, this is not just 2 to the 5th power. This is 2 to the 5th power to the xth power. Don't forget that x power. 16, that's on my chart too. 16 is just 2 to the 4th power. So in the place of 32 to the x, I put 2 to the 5th to the x. In the place of 16, I put 2 to the 4th. Okay, we're not finished yet because we don't exactly have the same base until I use my property of exponents. Power to a power, 2 to the 5x equal to the 4ths. Now I am right where I want to be. Same base, my exponents must be equivalent. So 5x must equal 4. Divide both sides by 5. And I got it. So my exponent here is 4/5. Is that okay? What I did was get the exponential expression by itself, make strategic substitutions. I substitute to give the same base. And once I have the same base, I equate the exponents and solve. All right, let's try another one. Solve the following exponential equation. Now here's where we're going to have to be think a little bit outside the box. Because you might notice in my chart, I don't have 1/2 to any powers. I could, if I wanted to, create it down here. But notice what I do have is 2 to certain powers. And notice that 8 is one of those chart numbers for 2. And here's what I observe. 1/2 is going to be my common base. So this guy already looks good. What I need to do, however, is substitute something for 1/8. And just as 8 is 2 to the third power, so 1/8 is 1/2 to the third power. So in the place of 1/8, I'm going to substitute 1/2 to the third power. But remember, this is just 1/8 right here. Now I got to take it to the second power. So here's my 1/8, 1/2 cubed. Taking it to the second power, I have exactly what I have here. So I have a common base. I need to clean up my mess a little bit here. I have powers to a power. So I'm going to multiply my exponents. 3 times 2 is 6. Look there. Same base. That means my exponents must be equivalent. So 3x plus 7 must be the same as 6. Subtract 7. Divide by 3. Again, not something you would expect. X is negative 1/3. So I have solved the exponential equation. Again, 1/2 to the first power is just 1/2. 1/2 squared means 1/2 times 1/2, that's 1/4. 1/2 cubed, 1/2 times 1/2 times 1/2. That's the thing I want to substitute for, 1/2 cubed. All right. We're going to fly low now because they're all going to be about the same. Let's see what I got here. Seven to the 5x minus 4 equal 1/49. Solve the following exponential equation. This one's going to require that we use one of our properties of exponents. Remember this guy? If I have something like a over b to the negative, a times b to the negative 2, I can simplify that by moving part of it to the other part of the fraction and changing the sign of my exponent. Remember doing that? We're going to be applying this principle as we examine this guy. What do you think our common base is going to be? Because this guy's a fraction, this guy's a whole number. Well, it's going to be what's already in the simplest form. 7 to the 5x minus 4. That looks really like it's ready to go for the left side. So here's what I'm going to do. I'm going to remind myself that 49 is the same as 7 squared. Hey, can I go ahead and equate my two exponents? No, because this is 7 to a power. This is 1/7 to a power. Completely different. But what I can do is use this principle right here and move this guy to the other part of the fraction and change the sign of my exponent. So 7 to the 5x minus 4 equals, move this up, change the sign of my exponent to -2. You could put it over 1 if you wanted to. No need to do that. Look what we've done. We now have exactly the same base. I can equate my two exponents. 5x minus 4 is the same as -2 plus 4 to both sides. Divide by 5, and I got it. So in this guy, we had to think outside the box again. We had to go, hey, I know what I'm looking for. I'm looking for 7 to some power. And I did it in steps. Changed my 49 to 7 squared. I want it to be 7, not 1 over 7. So I moved it and changed the sign of my exponent. All right, let's try this guy. Same thing. Here we go. What do you think the common base is going to be? If you guessed 2, you'd be right, because 32 is 2 to the 5th power. So I'm going to make a strategic substitution. In the place of 32, I'm going to put 2 to the 5th power. Don't forget, it's 2 to the 5th power to the -x power. And what's my exponent here? Make it visible. It's a 1. Hey, I got powers to a power. This is 2 to the 5 times -x is -5x equal 2 to the 1st. Identical bases. Exponents must be equivalent. -5x equals 1 divided by -5. X is -1/5. Again, not something you would anticipate looking at this, but something that we can figure using properties of exponents. All right, one more to go. This fella right here. Solve the following exponential equation. I obviously do not have the same base yet, but what base do you think you're going to work toward? If you guessed 10, you would be correct. This one's already in 10 to some power. Leave it alone. Can I change 1,000 to 10 to some power? You guys are probably familiar with this concept. The number of zeros you have in your expression gives you the exponent of 10. So if I have 100, what do you know? That's got 2 zeros. That's 10 to the 2nd power. If I have 1,000, that's got 3 zeros. That's the same as 10 to the 3rd power. Hey, in my expression, 1, 2, 3. I got 4 zeros. This is the same as 10 to the 4th power. So I just substituted for the 10,000. That's 10 to the 4th. Don't forget, that's taken to the -x power. All right, powers to a power, I multiply. Well, you know, I have identical bases. That must mean that my exponents must be equivalent. So I'm going to set -4x equal 3x minus 14. Notice from this point on, we don't even worry about the tens. Doesn't even figure in. Just looking at my exponents. So I think I'll move, get my x's on the left. -4x minus 3x, -7x. Hey, I'm going to divide by -7. -14 divided by -7, x is 2. So that's my last of 7.1 exponential functions and their graphs. I think you should be able to, without any problem, be able to handle these problems for 7.1. I will later, in fact tomorrow, post a video over 7.3, which is logarithmic functions and their graphs. Good luck.